Hello viewers, in today's session we are going to discuss another important problem from definite integrals, and in this session we are going to find out the value of this limit, that is limit h tends to 0, and here we have 1 over h and the integral from 2 to 2 plus h, and the integrand is square root of t square plus 3, and here we have dt, right? So here we'll see how by the application of fundamental theorem of integral calculus we can easily find out the value of this expression. So let us first quickly see the statement of fundamental theorem of integral calculus, which gives the derivative of the area function, right? So let us start. Now suppose we have a function, say y is equal to f of x. This is a real valued function which is continuous in the interval that is a comma b. So this is a closed interval, right? And if we have a function, say a of x, which is defined in some open interval a comma b, then the fundamental theorem of integral calculus states that the function a of x is equal to the integral a to x, and here we have f of t dt. Then the derivative of this function, that is a of x, that is d by dx of a of x, is equal to d by dx of the integral a to x f of t dt, and this derivative is equal to f of x, right? So the derivative of the area function a of x, that is a prime of x, is simply equal to the value of the function, that is f of x. So this statement is known as the fundamental theorem of integral calculus, and here we are going to apply this rule to find out the value of this expression. So now let us consider the function a of x as equal to the integral 0 to x, and here we have f of t dt, right? So here we are assuming a function a of x that is equal to the integral 0 to x f of t dt, where f of t is given by square root of t square plus 3, right? Okay, so now the derivative of this function a of x, that is a prime of x, should be equal to f of x due to this result, right? So now this function f of x can further be written by replacing this t by x. So we have square root of x square plus 3, right? Okay, now see here we have a prime of x. So let us apply the definition, the limit definition of derivative to a prime of x. So a prime of x can be written as limit h tends to 0, and here we have a of x plus h minus a of x divided by h, right? So here we have used the definition of derivative of a function. Suppose we have y is equal to f of x, then the derivative f prime of x is given by this limit, that is limit h tends to 0, f of x plus h minus f of x divided by h, where this h is a positive quantity and it is infinitesimally very small, right? So f prime of x is equal to this limit. So a prime of x is equal to this limit due to this definition, right? So now we have a limit h tends to 0. Here we have a prime of x. Now a of x plus h can be obtained from this relation. So here a of x is a function of x, and here we have the input x plus h. So replacing x by x plus h, a of x plus h can be written as 0 to x plus h, and here we have f of t dt, and a of x is 0 to x, and here we have f of t dt, and in the denominator we have h. So now let us focus on this the term that is in the numerator. So here we have 0 to x plus h f of t dt minus 0 to x f of t dt. Now here we are going to use a property of definite integrals, and the property says that if we have the integral say from 0 to a plus h, and here we have say f of x dx minus 0 to a f of x dx, and this difference is equal to the integral from a to a plus h, that is a to a plus h, and here we have f of x dx, right? So this is a very elementary property in definite integrals. So 0 to a plus h minus 0 to a is equal to the integral from a to a plus h. So here we have 0 to x plus h. So if we replace this a by x, then we have 0 to x plus h. For f of x, we have f of t, and here we have dt. Then we have 0 to x, that is 0 to x f of t dt, and here we have a to a plus h. So we are taking a as x, so we have x to x plus h, and here we have f of t dt. So replacing this difference by this integral, we can now write a prime of x is equal to a limit h tends to 0, and here we have x to x plus h f of t dt, and in the denominator we have h, right? Okay, so now a prime of x, this is a function of x, so a prime of x is now given by this limit, right? So let us now replace this x by 2, because here we have the limits from 2 to 2 plus h, and here we have x to x plus h, right? So replacing x by 2, we can now write a prime of 2 is equal to the limit h tends to 0. Here we have 2 to 2 plus h, and for f of t, we can now write square root of t square plus 3. Here we have dt, and in the denominator we have h, right? So we have arrived at this conclusion that this limit is equal to the value of the derivative of a of x at x is equal to 2. So now the value of this limit is equal to the value of a prime of 2, and a prime of 2 can be obtained from this result, that is replacing x by 2. So a prime of 2 is equal to square root of x square plus 3. So for x we have here 2, so this is 2 square plus 3. So this is 4 plus 3, that is square root of 7. So a prime of 2 is equal to square root of 7, and this limit has the value that is equal to square root of 7. So viewers, this is how by making use of the concept of fundamental theorem of integral calculus, we can find out the values of these kind of expressions using all these conceptual steps. Hello viewers, in today's session we are going to discuss another important problem from definite integrals, right? And in this class we are going to find out the value of this expression, that is limit h tends to 0, and we have 1 over h, and the integral from pi to pi plus h, and the integrand is square root of t square plus pi square over 2, and here we have dt, right? So we'll see how we can easily find out the value of this expression using the concept of fundamental theorem of integral calculus, right? So let us see how we can solve this problem. So now let us consider a function, say p of x, that is equal to the integral 0 to x, and here we have f of t dt, where our function f of t is equal to square root of t square plus pi square over 2, right? So here we'll assume a function p of x that is equal to 0 to x, and here we have f of t dt, right? So now from the concept of fundamental theorem of calculus, we can differentiate both sides with respect to x. So we have d by dx of p of x that is equal to d by dx of the integral from 0 to x, and here we have f of t dt. So this is p prime of x, and here the derivative of this integral, where the upper limit is a function of x, is equal to simply f of x due to the fundamental theorem of integral calculus. So now we have p prime of x is equal to f of x, and f of x can be written by replacing this t by x. So we have here square root of x square plus pi square over 2. So now this is an important relation, right? Okay, so now let us consider the definition of p prime of x. So p prime of x can be written as the limit h tends to 0, and here we have p of x plus h minus p of x divided by h. So this definition is used here because if we have a function, say y is equal to f of x, then f prime of x is given by limit h tends to 0, f of x plus h minus f of x divided by h, right? So due to this definition of derivative, we can now write p prime of x is equal to this limit. So now we can write p prime of x, and here we have limit h tends to 0. Now p of x plus h can be obtained by this expression. Here we have p of x is equal to integral 0 to x f of t dt. So now if we replace this x by x plus h, then p of x plus h can be written as 0 to x plus h, and here we have f of t dt, and p of x is given by 0 to x, and here we have f of t dt, and in the denominator we have h. Now from the properties of definite integral, if we have this expression that is 0 to a plus h f of x dx minus 0 to a f of x dx, then the value of this expression is given by the limit from a to a plus h. Here we have a, here we have a plus h, and f of x dx. So now we are going to use this important property of definite integrals to this expression, right? So here if we have 0 to a plus h f of x dx minus integral 0 to a f of x dx, then the value of this expression is equal to this integral from a to a plus h f of x dx. So let us compare this side with this expression. So here we have 0 to x plus h. So 0 to x plus h. So for a, we have x, and here we have 0 to x, 0 to a, f of t dt. Here the variable is t. So now the value of this expression can be written as, here we have limit h tends to 0. So this difference is now equal to this expression, that is a to a plus h. So for a we have x, so here we have x, and here we have x plus h, and for the variable x we have here t. So we can now write f of t dt, and in the denominator we have h. So now we have arrived at an important expression, that is the derivative of p of x, that is p prime of x is given by this limit, limit h tends to 0, integral x to x plus h f of t dt divided by h, right? Now let us replace this x by pi. So when we replace this x by pi, then we get p prime of pi, and here we have a limit h tends to 0, and the integral from pi to pi plus h, and here we have f of t dt divided by h, right? And this expression is the expression whose value is to be calculated, right? And for f of t we have square root of t square plus pi square over 2, right? So we have obtained this expression, and this expression is equal to the derivative of the function p of x at this point, that is pi. Now p prime of pi can be obtained from this expression. P prime of x is equal to square root of x square plus pi square over 2. So now p prime of pi is obtained by replacing x by pi in this expression. So we have square root of pi square plus pi square over 2. So this is square root of 3 pi square over 2, that is equal to pi times square root of 3 over 2, right? So here p prime of pi is now equal to pi multiplied with square root of 3 by 2, and the value of this expression is equal to p prime of pi, and p prime of pi is pi times square root of 3 over 2. So the value of this expression, that is limit h tends to 0, 1 over h integral pi to pi plus h square root of t square plus pi square over 2 dt is equal to pi times square root of 3 over 2.